Okay, gentlemen, this is where we ended last time, talking about continuity and discontinuity. So today, I just want to talk about two things, and that is finding the X-intercept and Y-intercept for rational functions. So we had talked about finding the X-intercept and Y-intercept for when we have regular polynomials or like linear functions, right? And we kind of saw that up here, if I still have it, right? We see up here, here's a polynomial, a regular squaring function, and we just factor it and we get our answers for our X-intercepts or our roots. And for the Y-intercept, we just plug in 0 and we get out our Y-intercept. Well, to find the Y-intercept of any function, you're always going to do that. So the Y-intercept is always setting x equal to 0. So in other words, the Y-intercept is always f of 0 is equal to whatever number. That's my Y-intercept. And many of us just knew it was like the back number. But if we take this function, and I'll take a couple more. If I take this function, I'm going to duplicate it, throw it down here. And then maybe I take this one where it's flipped over. Take this guy. Okay. Two functions. Now, if I were to ask you what the Y-intercept of these functions are, well, I would plug in 0, and I'm going to show a little bit of the work now, but we can kind of get a habit of what's happening. 0 minus 5, so I'm getting 0 minus 5. And on the bottom, I'm getting 2 times 0 squared minus 13 times 0 plus 15. So this simplifies to just a negative 5 over 15, so negative 1/3. So that's my Y-intercept. Writing it as an ordered pair would be this. Just plugging in 0 would give me a negative 1/3. And that's my Y-intercept, 0, comma, the number. There's only one Y-intercept. There's only one Y-intercept because of that vertical line test we talked about. At this value, at x equals 0, plugging in 0, x equals 0. There can only be one Y value that comes out of that. So I can only have one. I can go like this and cross the x-axis 1,000 times, but as long as I don't ever wrap back in on myself, I'm still considered a function. So a lot of times we get functions, and we're going to study this in the third trimester, that are cyclic. So they have one Y-intercept, but multiple X-intercepts. So we know when we're solving for the Y-intercept, we plug in 0, and I'm getting one value. Same over here. I'm going to plug in 0 to get my Y-intercept. 0 minus 0 plus 15 over 0 minus 5. Right, I picked the same function, and I'm just getting now I'm getting a 15 over negative 5. In this case, my Y-intercept is negative 3. So I can call this 0, comma, negative 3. And that's my Y-intercept for this problem. Right, so my Y-intercept is very easy to find. You just got to maybe do a little bit of algebra, a little bit of computation, but it's pretty easy to find. Pretty straightforward. I'll say straightforward, right? You're just plugging in 0 for all the x's. Whatever I have that doesn't have x's, I'm going to simplify that, and I get a number. Usually it's just, a ratio, something like that. X-intercepts, to find your X-intercepts, a little more difficult because we were just always factoring. But, how do I factor this? Or what do I do with that? So finding the X-intercepts is you solve. In other words, for most of the time, it's factoring the reduced function. Once we reduce it, we make it easier. We know what the graph will look like, right? If I kind of scroll up here for this one, I got 2x minus 3. That's what my graph looks like. It looks exactly like the line 2x minus 3, except there's this additional hole at the x value of 5. Right? And then I had the same idea up here, and over here was a little different. I actually didn't get an x-intercept here, right? A little bit of a different one, because I see this is like a fraction. This is a little bit of a weird one. So it's like I don't know what happens here, and there's still some kind of toying with we have to do, because this function doesn't actually touch the x-axis at all, right? Kind of like this vertical asymptote we have at 5. It almost looks like we have another one at 0, but we don't know why yet. Right? But so for the time being, you're going to solve the reduced function. I'll just say, like, if you can. If you can. So for your homework today, or classwork today, I'm going to give you ones that you, most of them that you can. Most of them that you can, but I'll give a little pointer to those of you that are following along pretty good and maybe grasp the math a little faster. You can have, and this is like, if you don't get this right away, we're going to do this next time, but you can have a horizontal asymptote. We're going to talk about this a lot more later, because there's a simple rule, and then we go into like the limit of the function. Like as the function goes on with x forever, what's going to happen to it? And that's the idea of a horizontal asymptote. But a lot of times this will like skip, or the horizontal asymptote will be at 0. So you like skip that whole x-axis, and it doesn't actually ever touch it. So it jumps over it like we do with vertical asymptotes. So it can get a little tricky there. But for the most part, how would this look? Well, let me give you a kind of a basic one. So most of the time it's when we're able to actually solve it, is if there is either no denom or my denom cancels. I'll say my denominator cancels, right? If my denominator cancels, then it gets a lot easier. Right, so a lot of these ones we're going to do are not going to have kind of infinite discontinuities right now, just because I want to get into the habit of knowing infinite, removable, and x-intercept. So a little bit of give and take on this homework. But if I give you something like this, like x to the third minus 3x squared minus 10x all over x, and something similar to this was on your homework last time. But if we're looking at this, what I'm saying is, okay, so first step, same one every time. What's my domain? Looking at the bottom, what is the x value that I cannot use that will make my denominator 0? Well, since it's x, I can't use 0. Plugging in 0 gets me 0. Now I see, can I reduce? And I use this to find out if I can factor, what my intercepts are going to be. I have a lot of stuff that can happen here. But I'm canceling out that x equals 0. Right? 0 can't be used. So I'm left with x squared minus 3x minus 10. That's my reduced function, reduced. Okay, since I'm able to cancel out my 0, my x, I have a removable discontinuity at x equals 0, right? I'm skipping the number 0. Skipping the number 0. Now, if I were to say, what are your x-intercepts? Well, we have over here, actually, I'll skip down for one sec. We have no infinite discontinuities here. Why? Well, I canceled, and now I have no more denominator, which means there's no infinite discontinuities. No infinite discontinuities means that there's also no vertical asymptotes. They are one and the same, so if I don't have one, I don't have the other. They're the same thing. X-intercepts, like I said, would be taking the reduced function and solving. Well, this looks like a parabola now. So now I'm looking for two numbers that multiply to 10 and that add to -3. There's my reduced function factored. And I'm getting 5 and -2. Obviously, those are numbers I'm allowed to get because the only number I'm skipping here is 0. 5 and -2 are x values I'm allowed to use because they're in my domain. So that means those are my x-intercepts, 5, 0, and negative 2, comma 0. What about my y-intercept? Sometimes I do this in a different color to make it stand out. My y-intercept, well, I'm going to plug in 0. I take my function, I plug in 0. My original function, right, my original OG function, 0 cubed minus 3, 0 squared minus 10, 0 over 0. And then I'm looking at this and I go, wait a second, I got 0 minus 0 minus 0 all over 0. What is going on here? I don't understand what's happening. I can't use 0. I already said that. And a lot of times I myself forget this, right? I forgot that 0 wasn't allowed to be used. It is a removable discontinuity. So my parabola literally looks like this. Well, here we go. Here's negative 2. Boom. Here's 5. Here we go. 5. And I know that it looks like it's going to be around 10, right? It would look like it's going to be at negative 10. So it's going to look like it's somewhere around here, but it's actually a hole in my graph. Negative 10. But there's a hole there. It actually does not cross there because 0 is not in my domain. Right? So we get very, very, very interesting graphs. It looks like a parabola because that's my reduced function. It looks like it has these two X-intercepts. It does because it's my reduced function, but it actually doesn't have a Y-intercept. And I can't have, there's no other one because there's no other point up here. My graph is not supposed to, have two X values or two Y values from an X value, but it also can have neither. And this is an example of neither. Okay. So kind of a weird one there. I'll do one other quick one. If I take a function, I make it a little bit easier. Let's say x squared minus 2x over x. I'll do it like this. I'll do x squared minus 2x. I'll say minus 15. I'll make that a plus, and I'll make this over an x minus 3. Okay, first step is my domain. The value that makes my denominator go to 0 is 3. I look to see if I can reduce this fraction to numbers that multiply to 15, and that add to positive 2. Here we go. I'm able to cancel these out, so my reduced fraction is, or my reduced function is just x plus 5. I was able to cancel out removable discontinuity at 3, right? My one issue, I was able to remove it, to fix it, to cancel it. I don't have any infinite discontinuities. Again, I'm not going to do as many of those because you can't really get X-intercepts. Not always, if there's still something on the bottom. Usually there's a problem there. So there's no infinite discontinuities, which also means there's no vertical asymptotes in this particular graph. Asymptotes. They're one and the same, and because now I have my denominator is just over 1, right? This function now is just over 1. I don't have any infinite discontinuities, which are vertical asymptotes. But my x value, my x-intercept, normally what I have to do is take the function, set it equal to 0. And this one is like, well, there's no x squared thing. I could still do it, right? I set the function equal to 0, right? I replace f of x with a 0, and I'm getting a negative 5. It's kind of a weird X-intercept, but it's kind of a basic function. So you just subtract the 5. Whoops, this should be an x. Right, equals x. There's my X-intercept. Negative 5, comma 0. Plugging in negative 5 will give me 0. Yeah, it's actually almost so easy. It's a little tricky. And then my Y-intercept, take the original, 0, and I'm plugging in 0 in original. And I'm getting 0 squared plus 0 minus 15, very nice, over 0 minus 3. And I'm getting negative 15 over negative 3, and I'm getting 5. Positive 5. It just so happens it is this number, right? But this is like mx plus b. So if my y-intercept is a positive 5, right, and then my x-intercept is a negative 5, it's the slope of 1. So it kind of makes sense, but that's just an example of one, right, where I'm taking I'm doing my same steps, right? I'm making y, so I'm taking f of x, and I'm making that equal to 0 here, and I'll do that in orange, right? I'm making f of x equal to 0. So I'm making y equal to 0, and that's how I get my x. But in this one, I'm making x equal to 0, and that's how I get my y value, right? It's plugging in the value x. So just a quick graph of this function. It is a y-intercept of positive 5. Positive 5. My x-intercept is negative 5. It just so happens to be the same number. That's because it's such a basic function with the slope of 1. Here's my graph with the slope of 1. Okay, I had a removable discontinuity at 3, so that's somewhere over here. And that means there's like a hole in my graph at that number of 3. No vertical asymptotes, which are no infinite discontinuities. There's what I'm looking at now. Regular linear function. And I've drawn these last couple totally by hand. I knew my x-intercept, my y-intercept. I knew there was a hole there. I have a pretty good idea of what my graph looks like. Okay, so that's what our next assignment is going to be on. It's kind of working through the idea of being able to do most of the character of the function analysis by no calculator. And then when I'm back in class, we'll do a bunch of it through the calculator.